So yeah, so we were talking about transportation elements, and one of the takeaways from yesterday's lecture was that we tend to assign more blame to the driver than is warranted, I think. So I think that's a good takeaway. And as I was saying, that leads us to kind of get too excited about what automated vehicles can do for us. And I'll give you one statistic to kind of go with that. If you look up, how many fatalities happen, and don't get me wrong, there are too many fatalities happening on our roads. There's no question in my mind about that. But what I want to say is that if you had to guess how many fatalities happen per million vehicle mile driven, that's the question I want to ask you. Let's say California, for example, right? How many fatalities in California happen if you normalize them by, let's say, 100 million vehicle mile traveled? What would be your guess? Yes, please. 50,000 per 100 million vehicle mile traveled. Okay, so I'm going to just write it down just so we have it on the record. And I'm not sort of talking just for my own sake. I want to write down 50,000 fatalities per 100 million vehicle mile traveled. Okay, so I'm not taking numbers up or down, more or fewer than this. Per 100, obviously normalized by 100 million vehicle mile traveled. Go ahead.
I was going to guess, 7.
7. Okay, that's a big sort of variability here. Okay. All right. So now we have sort of two bimodal answers, right? One is 7 per 100 million vehicle mile traveled, and then we have 50,000. Okay, where do you fall on that spectrum? You're getting closer to 7, 50,000, somewhere in the middle. Thoughts? More guesses?
I would say more than 1,000.
Around 1,000 or more, a little bit more than 1,000? Okay, so we got like 1,000. So maybe not quite 50,000, but in thousands, right? So something, yeah, okay. So again, we're measuring them all per 100 million vehicle mile traveled, so 100 million VMT, right? Okay, so what we're going to do is the obvious thing. We're just going to, Google search is not very useful these days, but I think we can probably look that up, okay? So let's just kind of do our big review. So traffic fatalities per 100 million VMT. Let's see. Hey, how about that? You've seen a number? Yeah, fatalities, deaths per 100 million vehicle mile travel. It's actually even lower than 7. 1.38. What did we learn from this experiment, right? We tend to exaggerate or overestimate how bad of a drivers people are in general. But if you actually look at this data, this is all California data, right? We're looking up. Now, if you look at this data for school bus drivers, it's actually 1/6 of that number. I think even lower than that number. So the actual number is only 1.38 per 100 million vehicle mile traveled. It's a pretty low number. And it's going to be very, very hard for any machine to top that, actually. To do better than that, having fewer fatalities than this number, it's a tough ask. It's a task that we potentially underrate, like in its difficulty, but it's a very, very difficult task to be. I think to me, what this number tells me is that, our roads are, maybe not great in design, but what we do is we just drive too damn much, right? We just drive so much. So if you were to think about we could potentially cut down our fatalities quite a bit if we could somehow reduce the number of people driving. And then there are obviously specific situations where the driving causes more fatalities or whatever. But again, this is a very, very low number. And even on some of the more sort of high hazard state, would you think is Arkansas is one of the states where this number is pretty high. That number is like 1.80. So it's still higher, but not quite as high as what we were thinking about, even in the range of the lowest of our estimates here, right? Yes, Matt.
There's a significant difference of Arkansas population in the
Yeah, so I think these numbers are statistically significant. If you look at, like, if you sort of run some statistical test on, whether this is sort of random differences, what are some systematic differences, I think you could see some systematic differences. I think part of that comes from more drunk driving. There is those factors that have, and there is basically more seatbelt usage. I think those things are important as well. And then part of it is just general affluence as well, right? You just have more cars that are newer and safer and all of that. So there are some actually, so if you look at the statewide differences, so Max asked the question, if there is some statistically significant difference between different states. So yes, the answer seems to be yes. And I think there could be many causes that we can attribute it to, but yeah, there does seem to be some systemic differences that lead us to kind of look at that number. And then if you think about this is sort of, US where fatality numbers are high to begin with. But again, if you normalize by million vehicle mile traveled, we are sort of middling rather than the absolute worst. So I feel like a better approach for us to traffic safety might be if we can create infrastructure that doesn't require as much driving. But that's a very challenging task because it's just not on traffic engineers. It's also on planners. What's our land use is going to be like? Are we going to be able to build housing where we need to build housing? All of those questions are way more complicated than traffic engineers' purview, right? So that's the challenge. So that was the big takeaway from what we were talking about the other day. And we're going to continue some of that discussion today too, but I just wanted to bring that up to kind of think about, and this sort of relates with this broader societal issue with, like, what does automation is going to do? And I just today, I came across this study and I didn't have a chance to kind of go through it, but Cruise, it's one of the companies that is, experimenting with robo-taxis in San Francisco, and I believe in Austin, they came out with some numbers about, what these numbers look like for 100 million vehicle mile traveled, the fatality numbers, the injury numbers, and all of that. What do they look like for their automated driving? I haven't had a chance to delve into that, but again, my prior on that, and I could be wrong, but my prior on that is that it's very, very hard to improve on these numbers. So I think maybe we have a less of a technological issue than more of sort of a land use planning, urban planning, and traffic design issue. So something to kind of think about there. And again, as I said, this is on untrained drivers. And if you kind of take the trained drivers on this, like school bus drivers, that number is like a sixth of that. So I think it's 0.2 fatalities per 100 million vehicle mile traveled. So it's a pretty interesting number if you think about it. So this is where we were. So let's go back and pick up this discussion on. So we were talking about some of the dynamic characteristics of vehicles when we left off. So let me go ahead and do the slideshow thing here. I think we need to put videos. Video. Okay. And again, this is sort of the curve. Oh, some days it works really well, some days it doesn't. Show this. Okay. Next up we have is this, we were talking about dynamic characteristics, and one of them we talked about was sort of just acceleration, where you have the cars having to accelerate to a certain value. And then this is about the trucks and what happens to truck speed as they climb the lanes, climb an uphill grade. And you could see that even if the truck started at 70 miles an hour, if the trucks are starting at 70 miles an hour, the speed comes down pretty significantly if they're traveling like an 8 or 9% upgrade. And then based on that, you can decide, and this plays a pretty important role on when we are doing level of service analysis or freeways, for example, right? So if you have certain percentage of trucks that are significant in nature, then, and you have like maybe let's say just 2 lanes in each direction on a freeway, or or if you have more lanes than you obviously have as a car, option to change lanes and go faster, and that is okay in terms of highway capacity, and you could probably maintain a little bit higher level of service. But if you only have, let's say, 2 lanes, and you don't have a lot of opportunities to change lane, then the level of service gets pretty significantly impacted, because you have the factor for heavy vehicle goes up pretty significantly. And the reason comes from this exact curve, which is the speed distance of trucks on upgrade. And then this is US customer unit. So it depends on how long your upgrade is. So for example, if you have a short upgrade, something like a 1,000 feet or something. So this is dividing it to 1,000, 2,000. So it's about 1,000 feet. So if it's a 1,000 feet upgrade, then a truck speed will only come down from 70 to about 50, which is manageable. But then you could see that if that grade was like something like 10,000 feet, like getting closer to about 2 miles, then so then the trucks will be traveling at like something like 15 miles an hour, because it's just going to be that much harder for them to maintain any kind of big speed. And they would have to almost be driving at that 18 miles an hour speed. And you could see that these curves sort of flatten out. And then these are different grades here. So 0% is flat grade. So on a flat, they can maintain 70 miles an hour. That's fine. And again, you'll have to be careful the context you're dealing with, because in California, anytime you're towing or you're a truck, your speed limit is automatically 55 miles an hour, right? So then you won't be starting at 70 miles an hour. You would probably have to look at a different curve, different dynamic characteristic curve, and what that does to your speed and all of that. And in some cases, that might work out better for your level of service, because again, if you're already at 55, certain grades just won't affect your speed all that much. So you will be able to maintain that free flow speed for that highway, because again, you're kind of starting out at a low speed to begin with. So in terms of level of service, sometimes that could work out. Yes, go ahead, Matt. Yeah. Right. So question is, so we've been mentioning level of service quite a bit, but then in planning, for planning purposes, they're switching a lot of these things to VMT being the measure that we are using now. So let me go back, right? So anytime there used to be development, right? And this is something that I used to do when I was an intern back in Florida in year 2002, 2003, that time frame, 2002 to 2005 almost. And that was a period of sort of, somewhat of an economic expansion in Florida. And a lot of the work that I was doing was just sort of assessing traffic impact. And we were always assessing traffic impact in terms of level of service. What was happening to the automobile level of service on certain roadways, right? And then for mitigation, what do you need? So in a lot of cases, what you needed for mitigation was more lanes, more right turning lanes, more left turning lanes, more sort of widening of the roadways and more lanes and all of that. And we were recommending those solutions all the time, right? So that the shift to VMT is a recognition of the fact that that's not a sustainable strategy, that we cannot just keep adding lanes, right? And that's always going to be a problem if we keep adding lanes just because, the traffic for 15 minutes of the day used to be a grade B level, and now it has deteriorated to grade D level, right, on city streets. So I think the switch to VMT is a valuable shift, especially in areas where when we are building any kind of infrastructure, and because if you keep at level of service being your measure of performance, then your answer will always come out to be add more lanes, add more lanes, add more lanes, right? So now what we are doing is we are switching to VMT, is that we are asking developers to be thinking about, could you do something else to actually fix this issue that is being caused by this new Burger King or new Target store or any kind of new housing, whatever? What can we do to mitigate that impact? Not by adding lanes. So that's why that shift happened. Now, that's not to say that, we completely discard level of service, because level of service actually in some ways could be beneficial to look at. And again, as long as you're not thinking about solution to B, always be at level of service A or B or C, right? So not always kind of adding lane to be your solution, but you still want to keep a watchful eye on level of service, because a couple of things. You might be thinking about, how are you going to evacuate a certain area, right? And then certain cases, even though level of service may or may not be your sort of a measure of performance, it could be useful in thinking about how evacuations might work in a certain area, or in rural areas, for example, where adding capacity may or may not impact your level of service at all, right? Or may not impact the level of service to the extent that it drives more demand, right? So improving level of service might be fine if you're not driving more demand, more automobile demand. And there's an interesting project that I'm involved with right now, is where we're looking at sort of rural areas or non-suburban areas where adding lanes or kind of adding capacity may or may not impact, or may or may not drive additional demand, what we call induced demand. And we're trying to figure out in what cases the concept of induced demand might be a valid concept, which it very well is in sort of urban areas and suburban areas where there is more development that takes place if you build capacity. But in sort of rural areas, outlying areas, there might be other mandates like wildfire evacuation that might be of more interest and more value than sort of being worried about those induced demand, because you'll think about this, right? So if you recall, I know it's kind of a tangent, but I think it's a good question to ask. So if you, let me see if I can get a whiteboard going. Okay. Was like a whiteboard thing. I thought there was like a whiteboard function that I used to use. Recording. Okay, so let me just go ahead and create a new slide here. So let's think about this, right? So let's say you have this speed capacity curve, right? So let's say this is what your curves look like, and then I'm trying to draw speed flow curve. Okay, so I'm going to try to draw speed flow curve, and in real world, speed flow curve looks something like this. It remains straight for a while, and then it drops at that point, right? So sometimes what happens in rural areas is that so it goes straight, and then it drops when you approach capacity. And on the x-axis you have, so if you look at this curve, on the x-axis you have the flow, and then or demand, and then on the y-axis you have speed. And then you could see that speed remains constant for a while, and then it drops as you go down, as you approach capacity of the road. Now, in rural areas, you might be on this part of the chart. You might be, like, for example, you might be in this part of the chart. And then if you add capacity, now you're in this part of the chart. So you're not actually impacting speed. So that means you're not actually impacting travel times. And so in this case, because you're not impacting travel times, you might not be adding additional demand, because additional demand comes from if you actually reduce the travel cost, right? But in urban areas, it becomes a big difference, because in urban areas, you're mostly operating over here at capacity in a lot of times during peak hours. And then if you move to this area by adding more capacity, then now you're actually you're improving speed. That means you're reducing the travel time, and reducing the travel time would induce more demand, right? So that's a interesting sort of question. So I think that shift to VMT is pretty valuable, but I just keep coming back to that question, right? As transportation professionals, as traffic engineers, we have to be aware of the context, So the context is pretty much everything. If we try to fit in this one-size-fits-all solutions, they don't always work. So I really am hopeful that we will switch to VMT in as many cases as possible, but then we still be aware of the fact that VMT is not something that we have to be applying everywhere. We don't always have to kind of think about VMT and induced demand in all contexts. There might be contexts where they may not be, the most applicable concept to be aware of. Okay, I hope this tangent was helpful. So yeah, so I think again, we'll still do some level of service analysis on weaving sections, because again, these level of service also relates in a lot of cases with safety too. So if you cannot be on that capacity curve, on the edge of that capacity curve on the speed flow diagram, that might be a good thing from a safety perspective too. So sometimes, and then we don't always have to add lane miles or add capacity to improve operations on the freeway. So we could improve level of service through ITS systems, by providing better information to the drivers, by doing some demand management and things like that. So those are other tools that we have that we could also use. So LOS estimation and trying to improve LOS by other means could also be a valuable exercise anyway. Okay, so let's go to the next slide here. Okay, and then speed reduction on upgrades. So this is you could have a speed reduction of as much as 30 miles an hour if your length. So this is another way of representing something similar, but now critical length of grade for design. So this is sort of your acceptable speed reduction that would be available to you. So if you're dealing with an 8% grade, you want to have a speed reduction of no more than 30 miles an hour, because obviously on 8% grade, you would see a lot of speed reduction, right? But what's your acceptable value? So you want to be sort of on the edge of this curve and not go to the right of this curve. And that's acceptable thing. So again, so if you want to, so this curve sort of define what your acceptable speed reduction is going to be. So if you're talking about, let's say, a 2% grade, you're going to be okay with providing like a 2,000 feet grade and a little bit less than 2%. So let's say if you're talking about a 2% grade, we are okay with a 5 miles per hour reduction. But if you're talking about, let's say, an 8% grade of 1,800 feet, then you could accept a speed reduction of up to 30 miles an hour. You don't want that to be higher than that. So this is sort of critical length of grade for design. And then this is for a typical truck. And we assume that the entering speed is 70 miles an hour, right? So these are the curves applicable for freeways, because that's where you assume that high of a speed. And you could figure out what would be your acceptable speed reduction. And acceptable speed reduction would be anything to the left of those curves, depending upon depending upon the context that you're looking at, right? So, and again, you could accept a larger speed reduction if you have a truck climbing lane, for example, right? So then you could accept a larger speed reduction because the trucks can actually simply move over to a right-hand lane or something like that. So as long as, so for example, on Cuesta grade, that acceptable speed reduction, because now we have that truck climbing lane, because we have a lane on the right side, and then on the coming downhill as well, we have another lane. So those will make, that you could work with that grade rather than having a lot of big congestion on that road. So climbing and passing lanes, where should we add those climbing lanes? So there are some sort of formulas for that. So there are, I'm going to talk about those, like, where should we add climbing lanes, especially on 2-lane roads where there is significant upgrades. We need climbing lanes. And then, because it's not necessarily that we are trying to always speed up cars, but it's also a safety concern too. Like if there is a big line of cars that happens, and then you have sort of these no passing zones, these double yellow lines, solid yellow lines in the middle. A lot of times people will ignore those signs, right? So you want to be on the edge of that. And that's what makes it very complicated, right? So the complication comes from the fact that you want the drivers to be at a manageable speed, but if you frustrate them too much, they will just simply start ignoring your double solid yellow line and start to go on the other side if the queues become too long. So that sort of is the challenge there. And then we always have these, when we have these climbing and passing lanes, we have to make use of the proper signs. Make sure that the signs are in good shape, not sort of moved up because of some malfunction in your hardware. Your slower traffic, keep right sign. Truck traffic, use right lane only. These are all signs that we need to make sure that we are providing appropriate guidance. And then this is sort of passing lane length. So whenever you need passing lane, So this is your requirement for when you need it. If your one-way traffic flow rate is between 100 to 200 miles an hour, you need a passing length of 0.8 kilometers. And then, so we could probably look at this one. So half a mile length is needed if you have one-way flow rate of 100 and 200. And then as this number increases, you need longer passing lanes. Okay, then you need so you need longer passing lanes of up to 2 miles if you have one-way flow rate of 700 to 1200. So anytime, so this is sort of gives you an idea about when you need those passing lanes, right? So you definitely start to look at that when your one-way flow rate exceeds 200 vehicles per hour. And then you need some taper. Taper is sort of the transition between where you have the passing lane or where you don't have it. And this is the formula for that. Your speed limit is higher. It's W times S, where W is the width of the road, width of the lane. L is the length of the taper. So taper length is basically just, where the 2-lane reduces from 2-lane width to 1-lane width. Okay, so that's your taper length. That's your L measurement. And you could get it from WS. And then if speed limit is 45 or more, then it's just W times S. That's your length. And then if it's less than 45 miles an hour speed limit, then it's WS squared divided by 60. Yes.
Doesn't this equation vary by state?
It does vary by state. This is the AASHTO guideline. I think California might as well have their own
California uses that, but I'm familiar with like Ohio uses 50 instead of 60.
Right. So yeah, so that's actually, so this is another interesting point is that a lot of states have their own design manuals. For the most part, for this class, we're going to just kind of focus on the AASHTO guidelines, but there is a big, discrepancy in some cases between how state do things in terms of highway design. So yeah, that's absolutely correct point, is that some of these equations vary by states. And that absolutely does happen. So don't be surprised if you see some other equations kind of coming into play. I'll give you another example. California uses a lower height of the object when they're talking about passing sight distance in California. So on state highways, that means that they require way more passing length. The passing distance in California, if you estimate using the California Highway Design Manual, it comes out to be much higher because they assume a much lower object height of what you should be able to see, right? Compared to the AASHTO Green Book guidelines. So a lot of times, you could write design exceptions, and that's what Caltrans does a lot of times. They will just write design exceptions to sort of match with the federal guidelines, and that's in most cases that is acceptable, right? So that California does that all the time. California engineers will do that, and then there is some push for sort of changing the design standards, and that does happen over time as well. But again, that process does take time. So that's a good point, right? So you have to be aware of the jurisdiction that you're operating in, and there are changes based on the jurisdiction for sure. Okay, so in terms of how we are going to make use of this information, so what I'm going to do is over the weekend, I'm going to start posting some homework problems for you. And I'll basically post the whole homework assignment for you over the weekend. And then you'll have some time to get it done. You won't be able to solve all the problems because we wouldn't have done all the homework. But there are going to be some problems that relate with the content that we've already covered. And I'll point that out to you guys. So you can start working on some of the problems for your homework number 1, okay? So I'll do that over the weekend, and you'll start to see some applications of these formulas, some questions that we've been dealing with. There might be some sort of thinking type questions involved as well. So kind of just the discussion that we've been having, some questions around those as well. But again, you won't be able to solve all the problems, but you'll be able to solve some of the problems starting this weekend because we would have covered some of this material, including these formulas and things like that. Okay. So drivers are a big, element of the road because, as you said, we probably tend to overestimate their role in causing collisions and crashes, but still, I would say that they are an important part of the roadway. When design is incompatible with the capabilities of drivers, the chance of error increases, right? So we have to make sure that, we are minimizing the chances of error. We're making sure that the drivers are, in fact, paying attention to the road. And then this is something that they do, right? For example, if you look at the highway between Los Angeles and Las Vegas, right? It goes through pretty flat areas, and they would introduce some curves on the road just to kind of get the drivers to pay attention a little bit. So if you look at that highway, you will see some curves that you would think, why do we actually need that curve? That just makes the alignment a little bit longer, maybe increases the cost of construction, all of that. But they do it to make sure that the drivers are not always just so bored driving like in a straight line all the time, right? So there are things that we need to do to make sure that the drivers are paying attention. So we always want to somehow design to minimize the chance. We don't always do that, by the way, right? So we don't always do a great job of this, but this is something that's one of our goals, is to kind of consider the human factors to design in a way that minimizes the chances of error for our drivers. So important topics about drivers. 3 things we are going to discuss here. Reaction time, because remember, and then this is where sort of technology can most help us, right? Is that they can reduce the machine can potentially react much quickly, way more quickly than a human driver can, right? So that sort of is the, let's say you're driving in the red car, and let's say if you're, maybe I'm too loud, closing the doors. Okay, maybe I should close the door. Excuse me. All right, so we're talking about reaction time, expectancy, and some older drivers issues. So these are the 3 things we're going to sort of deal with a little bit in this lecture now. So one of the things that is to think about is reaction time, and we go over that a little bit in CE 321. But the idea is that, let's say you're driving in this red car here, and you see this blue car is stopped along the roadway, or it's braking, right? So it's maybe starting to brake. So as the follower, you won't start to brake right away, right? It'll take you some time to kind of look at what they're doing, what the car ahead of you is doing, and then try to slow down. So between the time that you're seeing something and reacting to it, that's the time you're actually just traveling at the same speed that you were at before, right? So this distance is called the reaction distance, right? Where you're still traveling at the same speed as you were way beforehand, right? And then you stop, then you start to brake, and then hopefully you brake before the blue car brakes. And then for whatever reason, blue car is trying to brake, right? So there is that reaction, and then there is the actual process of braking that depends on the braking capabilities of your car and all of that. So your stopping distance is actually a summation of the reaction distance and your braking distance. So we are going to do some examples of that in the class too. So there is going to be some homework problem related to that. And then we'll talk about expectancy. We want to create an environment where the drivers can accept. So we want all of our signs to be in consistent format, so that the drivers are not sort of fumbling around and what does it mean? What does it mean all the time? So the signs have to be consistent. They should always be, to the extent possible. And that's where it's sort of MUTCD. If you look at what is the full form or act for the acronym MUTCD, it's the Manual for Uniform Traffic Control Devices, correct? Right? So it's uniform traffic. We want it to be uniform because we want to make sure that the drivers and road users' expectations are met to the extent possible. And then old and young drivers, right? Teen drivers and very old drivers come with their own set of challenges. So we'll talk a little bit about that too. So this is sort of the reaction time idea. The results show that when an event is expected, if you have an expected event, the reaction time for drivers could be as fast as 0.6 seconds, right? Some drivers might take longer to react, maybe, and that could be because they're distracted or whatever. And obviously, if you are driving under the influence, your reaction time goes up quite a bit and all of that. Unexpected events, the reaction time, if you don't expect certain events. So for example, if you're driving on a freeway, right? You're not expected to stop, right? Freeways are supposed to be where there is no signal, there is no stop sign. So you're supposed to be driving. So on freeways, your reaction time is necessarily going to be larger, right? But as you're approaching the signal, then your reaction time would be slower, right? So, and that's why you would see signs such as signal ahead, for example. So if you're driving on Highway 1, for example, right? It's a rural segment of the road, so you don't expect a lot of signals to come. But then suddenly, if you approach a city on Highway 1, then they would put up some sign that signal ahead or something like that, right? Or a population zone or a city traffic ahead or cross traffic ahead or whatever, right? They put that so that now you're expecting things, so that your reaction time could become a little bit better than what it was when you were not expecting. So some of those signs come from this idea that your reaction time is way faster if you're expecting things versus when you're not expecting things. Okay, so these are sort of the charts. For expected, it could be 0.6 seconds. So and then sometimes it could be as high depending upon what is the content that you are dealing with. So your action time could be varying, and then AASHTO Green Book and all our design manuals, they account for that in certain ways. They'll report what reaction time you should be using for certain reaction. So reaction time for baking is called PIEV time. It used to be called PRT in old manuals when I was in college, perception reaction time, but they have a much sort of more precise name for the time now. It's called PIEV. That kind of looks at that process and describes that process of what happens in human brain much better. It's called PIEV time, perception, identification, emotion, and volition time. And the volition is basically your reaction. So PIEV time. Literature suggests 0.6 seconds for average alerted driving, one additional second for normal driving, and some drivers could be as high as 3.5 seconds. AASHTO book default, Green Book default is about 2.5 seconds. So that's again like some kind of an 85th percentile number that the 85% of the drivers can react within that time frame. So how do we conduct a study to find the reaction time, right? So how do we actually figure out that these values, who figured out these values? Where do these values come from? So what I'm wondering is that, what do you think? Like, what are some of the ways that one could think about estimating these times for a population of drivers? What kind of study can you do to figure out what is the reaction time for drivers? Any thoughts? Yes, please.
You do simulated studies?
Yeah, you could do what we call the driving simulation, where we have pretty extensive setups in some locations where you have the drivers, you develop your simulation scenarios, and they react to it. And obviously, it's not one-on-one, and you have to sort of somehow validate those things. But yeah, so I think you create as realistic of a scenario in a driver simulation setting. That's one way of definitely doing that. And then you could actually do some field studies as well nowadays, because you have these cars that you can equip with certain, certain, what do you call the technology, where you could start like when the braking happened, and then when the eyesight encountered a certain obstruction on the road and all that. So you could do that too. So simulation, driving simulator research lab, one way definitely do it. And these simulators are getting pretty nice. They can become very, very realistic. Although you see some issues like these sort of disjointed or discontinuous and non-continuous sort of elements on the road. But these things are getting way better all the time. And then you have sort of these vehicle cabs where you're driving. It almost feels like a game. But sometimes it could also give you some motion sickness too, because you're not actually moving, but your brain thinks you're moving. So for some people, that could be pretty challenging in terms of motion sickness. So that's one way of doing that. And then you could start thinking about, starting to conduct some study in the field. If you can monitor driver reaction, so kind of equipping the actual cars with equipment, and then just try to, obviously you're not going to put a drunk driver on the road, right? We're not going to actually do that. So maybe for drunk drivers, simulation might be the best way to study it. But again, you'll have to do a pretty robust study to be able to do that. So, there is a website here that you could click on and click the large button on the right to begin. Click here to start. And then as soon as the signal turns green, if you click, And this was a pretty quick reaction. So, okay, so you could actually conduct yourself, like how fast you can react to certain things. Obviously, this is a computer, but you could have some fun with it, right? If you're over 21, maybe you do this one time, and maybe have a few beers, then try it again, right? So that could be pretty fun. So that link is there. So let's go ahead and play with that a little bit and see what happens to your reaction time when you're drunk, right? So there could be some interesting, fun results there. Obviously, drink responsibly if you decide to indulge with that. But you get an idea about how slow you get when you're not actually paying attention. So something could be learned from that. And there are like these types of. So this is one of those, and there are other sort of green light reaction time tests that are out there. Pretty simple to build. Could be interesting. Yeah. So this is again, you could figure out that the reaction time can actually slow down when you're not fully engaged with something. So distance required to stop. So as I was saying, like you could figure out distance that is required for you to stop. It's 1.47 SI initial speed times T. Now this formula is an empirical formula because this has been normalized for units. So you could, and again, these notes are all online, so you don't necessarily have to copy anything, but you could figure out, and this formula is not necessarily for stopping because I'm giving you an initial speed SI and SF is the final speed. You just substitute final speed to be 0 if you're looking to get the distance that you require to come to a complete halt. Okay. In some cases, you might not be able to come to a complete halt, so you have to figure that out. But and then 0.348 is sort of the factor that you require based on what type of deceleration we assume the vehicles can generate. And this 0.348 is based on that you can generate 11.2 feet per second square deceleration rate. So if you assume that, based on that, you could figure out that your this factor would be 0.348. And if your deceleration rate changes, then you have to kind of come up with a slightly different formula. But for the most part, this is a good way of coming up with what type of stopping sight distance you require at all points on the road. You substitute SF to be 0. And then remember, you can plug in D as in feet, and then speed could be in miles per hour, and reaction could be in seconds because of these factors that you have already added on to it. Okay, so this 1.47 is nothing but a feet to mile conversion divided by hours to second conversion. So it's basically 1.47 is just 50 to 80 divided by 3,600. That's it. Okay. Any questions? So again, you'll have some example problems to work on this, and then we can talk about it in class as well before you submit the problem. So there will be some opportunity to practice using these formulas in class. Okay. Let's talk about expectancy. This is the second of the factors that we're dealing with. Unusual, unique, or uncommon situations that violate driver expectancies may cause longer response time, inappropriate responses, or errors. Okay. So let's look at this freeway exit, right? What do you think is the problem with this freeway exit that's denoted by these red arrows? You see any issue with this exit? Yeah. It's on the left-hand side, right? Most exits are on the right-hand side, but because this is on the left-hand side, so what do? We typically would warn drivers that next exit that's coming up is on the left-hand side. So maybe next time when there is a numbering for exit or how many miles that exited, they will put us another sign saying left exit or something, right? So what they were trying to do is sort of preparing drivers for that unusual nature of that exit, right? So we always try to do that. And the last one is the old drivers. Now, we are expecting as many as 22% of the drivers are going to be more than 65 years old by 2030. That's a pretty large number, almost a quarter. So that means that, we have to obviously think about that in terms of licensing, like whether we automatically provide license to drivers. And that's where there is some excitement around automation as well, right? We still want to give older drivers an option to be able to travel wherever they need to travel. So I like, don't get me wrong, I like what's happening with automated systems, especially if they're implemented in limited areas, as long as we don't think, we can replace all of our cars that are sitting on our driveways today will all be automated. I think that probably is not something we could probably achieve realistically, but in context, in limited context, in certain areas of the city, we may be able to provide where we can absolutely train the computer to be driving in certain contexts, in clear weather, all of that. Maybe we can make that happen. So in general, I like what Cruise is doing in terms of they've taken one city network and they're just sort of perfecting the technology on that city network of San Francisco. I think that's a good thing. That's a useful thing. But I think there might be some options for us to kind of take the older drivers away from the wheel so that they're not driving, endangering themselves and everybody else on the road. And what's the problem with elder drivers? This is the problem. Fatality rate per 100 million vehicle mile traveled. For older drivers, actually, you were onto something, right? So if you look at sort of the aggregate, because most drivers are in fact in the middle-aged, so that number actually could be pretty high, as high as almost more than 9 fatalities per 100 million vehicle miles for older drivers and for the teen drivers. But then as you get more, experienced driving, that's where sort of, things got to settle down. And the number kind of reduces to less than 1 even. Yes.
I was wondering, is it just experience?
Yeah, I think it's the driving experience, and then you get some wisdom. I think it's interesting to me, and I haven't looked at the recent research on this, but it's sort of interesting to me how the chart kind of goes down and then picks back up a little bit again, right? So maybe you got too confident in some ways, right? So maybe that has something to do with it. Yeah, maybe where you're driving. Obviously, it depends on the context too. Yes.
Whether that statistic for the age be related to the fact that different states have different age requirements for when people can get their license.
That's a good point too. So this is sort of an aggregate level statistic. If you look at, that could very well relate to when you're allowed to actually drive alone or drive with a passenger who is a licensed driver, when you can drive with your buddies, all of those things could play into it. But I think on an aggregate, this does show you that, the danger of very young drivers or very old drivers, that's definitely there. Yes.
Drunk driving too.
Yeah, there's definitely drunk driving too. Maybe that's where, you start to see that, that 20 to 24, maybe you just start drinking and then you're driving still, maybe it hasn't reached up to par, or maybe you're just prone to making more of those types of mistakes, right? But yeah, you're right. So, and you will see that in insurance rates, when you're a teen driver, talk to your parents, when you first get your license, you pay through the roof, your insurance premium goes through the roof at that point, and it gradually comes down. I think a lot of car rental companies don't even rent to people who are under 25. And that's all related to this. And I think on the other end of the spectrum, there's a lot of research on when do we need to sort of not renew automatically the license, right? So that's also related to this other end of the curve. So the age of the drivers plays a pretty interesting role there. Okay, so age affect drivers, the senses degrade, the vision and hearing, especially the vision, the peripheral vision degrades quite a bit actually. So you need to have, maybe if you have, so vision is a big issue, especially the peripheral vision. So driving through the intersections becomes pretty challenging for older drivers. The motor skills decline, so maneuverability becomes difficult. And then the cognitive issues, right? So slow decision-making, cannot divide attention, poor memory, some confusion kicks in as well. So there is a lot of things that can happen. This is another interesting question, right? So the amount of light needed to see an object doubles every 13 years. So by age 35, the drivers may need 32 times more brightness than they did at the age of 20. So pretty interesting statistic there as well. So again, nighttime driving could be challenging as well. So you might want to think about maybe for older drivers, maybe some restrictions on what times they can drive could be useful as well. So in conclusion, how do we provide a safe situation for older drivers? So here are some things, if you're talking about areas with high percentage of older drivers, simpler messages, wider pavement marking lines, larger fonts on size, brighter marking and signs, easier maneuvers somehow. So those could be some things to consider where you expect older drivers, maybe closer to a community that's retirement community and things like that. So you could see that this is sort of the signs are like, maybe bigger signs. So these are the sort of the new standards for design signs. So just kind of make it easier for the older drivers. So that's one way of sort of dealing with that. And then visual acuity. So you have to be very careful about whether or not your signs are visible. And this is where sort of new technology is becoming very helpful. A lot of agencies are now taking advantage of crowdsourcing to report this stuff, whereas before they had to kind of have manpower kind of monitoring everything. But there are some innovative agencies that are now kind of having the crowd people report those issues, and they're taking action much sooner. So you can see here that the vegetation outgrowth blocks the sign completely. That's an issue. And then the signs are being hidden and all of those things. So we have to be kind of making sure. And then the other thing is that if you look at, there is some human factor research that we talk about in traffic safety class, is that drivers a lot of times may not be paying attention to what you think they're paying attention to, certain segments of the road. They might not be paying attention to the most important part of the road, right? And we talk about that quite a bit in our safety class, but the idea is that maybe there is a speed limit sign or a school zone sign, but because there is so much else going on the roadway, that people start paying attention to that stuff rather than oncoming traffic or the most important sign on the road. So this is something that you should be concerned about as an agency, is that different segments of the road, when maybe the places where collisions are happening, maybe you make sure as a driver, conduct a study and see what the drivers are most focused on at that location. Is it the most important thing on the road? Or are they paying attention to extraneous things that are actually not critical from a safety perspective? So you have to think about those things. For example, here, the sign is hidden, so they can't actually see what the sign says here. I don't even know what the sign says, right? So you don't know what they're talking about here. So maybe, I think what they're trying to determine is like there is a driveway ahead of it, and people actually can't see what's happening in front of you. So different elements of the road and specifically accommodating older drivers are needed in certain contexts. So be mindful of that. So those are sort of what I wanted to talk about in terms of the elements. And in the next portion of the class, so I'm going to sort of stop here and ask you if there are any questions about traffic engineering elements that you want to talk about. Any elements that you think we should have covered in more detail that we didn't, or things of that nature? Any questions? Yes, please.
Wouldn't also better street lighting also help with the drivers?
Yeah, they definitely. Yeah, so we talked about that vision thing, right? So better street lighting is pretty important, and it's very, very important also from a perspective of what's happening to pedestrians on the road, right? So I was looking at a study, and I'm not sure if I can quickly find it. So I'm going to look at this chart here. That's pretty eye-opening, right? You mentioned lighting, very, very critical issue. Like if you look at this is the number of pedestrian fatalities by lighting condition, 2010 to 2019, so before COVID. And you could see that pretty much all of that increase, a big chunk, way bigger chunk of increase in pedestrian fatalities has come from dark driving conditions, dark conditions on the roadway, right? The daytime, pretty consistent, right? If you look at that number, it hasn't gone up. It has gone up some. I wouldn't say that it hasn't gone up at all. But look at what has happened to the nighttime number. It's went over 3,030, almost a 50% increase. The increase by 54%. The daylight pedestrian fatality only increased by 16%. Right? That's a pretty interesting number. And, so that means, we should be lighting up intersections as much as we can. Our street lights wherever especially where we expect pedestrian. And this also tells me that there might be some element of, and I don't know for sure, but some element of our housing issues that we are dealing with in our cities too. That might be another issue. If the unhoused people problem becomes worse and worse, there are more people who are on the road, on the street in the night times, and there might be something to that. And that probably, brings us to the problem. It's a sad situation of sort of not a lot of political will to kind of address that issue, because you think like it's just unhoused people who are being affected by this issue. So there is not a lot of political will on dealing with that issue. And I've seen some data on it, some interesting sort of research that came out recently on it too. So something to keep in mind. But but definitely lighting would certainly help that situation. Yes.
I think it's also like the general walkability.
Yeah. Definitely, there is that, but specifically dealing with what's happening in the nighttime. And again, maybe you're not expecting a lot of pedestrians in nighttime. Deal with that unexpected thing happening issue as well. So yeah, a lot of factors here, but I think all of those factors would be improved if we were to, we were able to provide all the street lighting. I think that's what it tells me. But one good news is that, that number is sort of, maybe we are in fact providing some, so between 2016 to 2019, that number did become somewhat constant after climbing from this number to this number pretty high. So that's something to consider, right? So yeah. And again, but if you look at the same time, what happened to daytime fatalities, they came down actually a little bit, right? But nighttime went up by a little bit margin. So something interesting to think about. Great question. Okay, so I'll clear this drawing here. So let's go back and see. So now what we've talked about a lot of different issues. Now what we're going to deal with is how do we actually address that issue through whatever means. So I think part of that is just collecting data. Like how do we collect data on different things? This is a traffic engineering class. If I don't know if you wanted to be here. So wrong class. So maybe, yeah, I guess that. So 4:30 is probably when your class starts. Okay, so let's see. Hide notations. So let's look at this second lecture now. So now we're talking about transportation studies. Like, how do we talked about so many issues, so many different elements. Now, what data do we need to be able to address issues that you might encounter because of those elements, right? So that's pretty important, and we collect a lot of data for that. So probably should say traffic engineering, transportation engineering. So what are some of the studies that we're looking at? So we'll be talking about some general introduction, and then we'll talk about traffic volume studies, pedestrian studies, traffic signals. So we'll do like a traffic signal warrant study. That sort of is going to be our next lecture, is kind of focusing on when we install the warrants. We'll kind of try to examine a little bit critically what happens there, and traffic signs and pavement markings, and how do we study those, and then speed limit studies, and that's something that's how do we think about speed limits is undergoing a pretty significant revision in our traffic engineering community. So we'll talk a little bit about that too. So first study that we're going to talk about is traffic volume studies. Pretty standard thing is counting, right? So we want to count cars, count pedestrians, count bicyclists that are there. So volume is the number of vehicles or person passing a point, entering an intersection, or using a facility during a specified time period. Now that time period could be daily, could be hourly, it could be annual, whatever, right? So it could be, but one thing is that difference between volume and flow, right? So let's kind of make sure that we think about this a little bit. So what I want to make sure that you think about is the question of volume versus flow. Does anybody know what's the difference between volume versus flow is? What is volume versus flow? Or flow rate? Yeah.
Volume is how many, flow is how fast. Or
Not quite, not quite. So flow is still measuring some kind of a volume, but a specific rate. Yeah, go ahead. It's volume over time, but anytime we're talking about flow, we're talking per hour. So volume could be hourly volume. So we could talk about hourly volumes. We could talk about daily volumes. We could talk about yearly volumes, whatever. But when we say flow or flow rate, we're always talking about volume per hour. So when we measure number of vehicles per hour, number of pedestrians per hour, that becomes our flow rate. So flow rate is always, so when we say flow rate is per hour. Okay, so anytime we're talking about, so you can think of flow rate being a special, so hourly volume or flow rate is a special case of measuring the volume. Volume counts are sample or actual volumes, right? So, so we'll talk about that. How do we collect that data? Okay. So let's talk about traffic count. How do we count traffic, right? In some cases, we might have to count traffic manually, right? We might have to count, in some cases, in some rural areas where you have issues with, maybe data connection, you don't have the good data connection, or you have concern about, maybe the equipment may get damaged that you might be putting in, maybe because of truck traffic, or maybe some, wildlife crossings, whatever. Could be any number of reasons where, manual count might be the best way. Just go out in the field and count cars, right? So that sometimes we still have to do. And hopefully, we talked about that in the lab yesterday a little bit too, right? So you're going to probably have to go out in the field, collect some data. So we should know how to collect the data, even though in a city like San Luis Obispo, we could probably make use of automated traffic data collection, so that should still be okay. But in some cases, manual might be the best way to do that. So we'll need some tally sheets, some hand counters, all that stuff. And then automated would be portable traffic counters, detectors and sensors, video cameras. Those are becoming pretty useful these days. Caltrans is using that a lot on their freeways. They have great cameras, and they just kind of, I think their MyoVision, I think, is the technology that they use, just sort of automated way of counting cars. And obviously, there's some validation that goes into it. You want to make sure that the counts that we're getting using that automated technology is in good shape, isn't correct, like, it can be validated. Oops. So this is what the traffic count at automated method looks like. So this is just a picture of those things. So we have these rubber tubes that we install on the roadways. We do that. We recently conducted a study on Cal Poly campus right after COVID. I think that was 2021, spring of 2021 or winter of 2021, around that time. We had tubes on the roads laid out, and then we just count how many people are coming in through what entrances and where they're headed. And there could be some sort of RFID type, so there could be some roadside unit, RSUs, along the side of the road, and then they measure how many cars are passing by. I think we were using these tube counters in our study. So this is what the tubes look like. We just kind of put those tubes in there, and then we just count how many. So these are connected to some roadside unit that you can basically pull out once you're done with the data collection, and it reports how many cars pass by. It can even classify whether it was a car or a buck or a bike or a truck. So all of that could be classified. So that's pretty neat. And you will actually see that if you are interested, if you're curious how that works, is that I think on the pedestrian bridge on California Boulevard, that technology is still available. You could see that they have placed the tubes there, and they just count how many bikes and pedestrians and are crossing that. I think they're specifically interested in the bike count to be able to demonstrate the value of that bridge. So once you kind of install these traffic volume studies a lot of these equipment, the traffic volume equipment is also capable of measuring speeds. So you could do both of those things. So you could see on this chart that you have, how many cars pass by, average daily traffic. It's a pretty rural area, I guess. There's only 35 cars per day. On weekend, there were 43 cars. Total ADT is 37. No trucks passing through there. Speeds are pretty low. And then you got the 85th percentile speed, 50 median speed, the average speed pretty close to, and then the top speed, the lowest speed, 10 miles per hour pace speed, which is just how many cars were traveling. What was the 10 mile per hour interval, which was used by most cars? So that was 20 to 29.9. So there was 67.3% of the cars were traveling within that 10 miles per hour interval of speed, right? So you could see this 20 to 20.9, 29.9 is the 10 mile per hour interval. And average truck speed, 22.2, average car speed, 24.5. This is interesting to me because I'm just now noticing they reported no trucks here. But there were actually 2 trucks, right? So that's a pretty small number of trucks. They did pick up some truck speeds, but they were sort of very small number of that. So they just reported them as 0 here. And then the traffic volumes, and then whatever number of, so they probably had the data for like maybe 7 or 8 days. And that's how they counted 265 cars on the road. Average axle is 2.1, so pretty close to 2. So mostly just 2 axle cars were passing by. And then you can see the gaps are just humongous here, right? Pretty large gaps because very small ADT, right? So I think this is the report of the car that we showed you, or the roadway location that we showed you in the previous slides, right? So it's this road probably where this data is coming from. Pretty rural, unpaved road. So some manual methodologies, tally sheets. What tally sheets look like is this. You just kind of, if there is a truck passes by, you just put a tick mark here. And then, if another truck passes by, you put another tick mark. Car passes by, you just sort of make a tick mark. So you could see, okay, I'm gonna just have 1, 2, 3. As cars pass by, you just count them. So 5, and then just kind of do the tally marking that we normally do. And then depending upon which turn they're making, right? If this is only for the right turners, left turners, through vehicles you count here. For left turners you count here. You just start putting where they're coming in. Now again, if it's a complicated intersection, you might need more than one person to do this type of data collection manually. And then there are actually boards that come in where you can actually just press a button rather than having to kind of control the markings. So there are those technologies available. I think I could probably show those to you as well. So this is mechanical count board, so you can just press buttons rather than having to always, and then these buttons sort of, right, through, and left, and it automatically that kind of fills out that tally marker. So there are those types of technologies. So these are sort of mechanical counting boards. Newer ones are more electronic, and then these are pretty commonly used as well. You just kind of take these equipment, plug them into a PC, and they generate the kind of report that I just showed you. And so this is kind of what you could see. Right, through, and left. These data sheets get generated all the time. And you could see that, this is sort of sample of traffic volume diagram. You should be able to look at this diagram and tell me this is northbound. So hopefully all of you can tell me what's the northbound left turn volume according to this chart. Northbound left turn volume. What's that? 182? Yeah, that's the right number. Because if you say northbound left turn volume, that's right here. Northbound through volume is 642. Northbound right turn is 300. So you can do the same thing with southbound or eastbound or westbound. And then total intersection volume is 5646. It's basically you're adding up all the entering volume, and that's how you get it. Sample of traffic volume diagram. Again, this part of the diagram is just phasing diagram, signal phasing. We'll learn about that later, right? But this is traffic volume diagram. Again, very important for for timing the signals and all of that. So we have to always be collecting this type of data. This doesn't have any kind of pedestrian volumes as well, but we have to report those as well. So the question becomes, what time should we collect the data and all of that? So now that we have some idea of what the data looks like, in the next class, we start discussing when do we go out and collect data? What are the implications of collecting data over the weekend versus weekdays? So we'll kind of start discussing those questions and be on the lookout for some homework problems that are coming your way over the weekend, okay? And they won't be due until like maybe on a week, 10 days or something. So there will be plenty of time to work on those, but just be on the lookout for those, okay? If you have any questions, let me know. But if not, then I'll see you on Tuesday and we'll kind of pick up this discussion again.